Imagine taking all the gold hidden inside our planet and spreading it out across every single landmass on Earth. You'd end up wading through a solid, shimmering layer nearly half a meter deep, but you can't reach any of it. That vast fortune is locked away 3,000 kilometers straight down, trapped under millions of atmospheres of pressure inside the planet's core. To understand why it is down there, we have to look back 4.5 billion years. Early Earth was essentially a giant droplet of magma in space. As it cooled, the heaviest materials naturally sank toward the center. Dense metals like iron and nickel plummeted inward to form the core we know today. Because gold is a siderophile, an element that naturally binds with iron, it went right along for the ride, leaving the upper, rocky layers stripped of precious metals. This creates a strange geologic paradox. Geochemists estimate that more than 99% of Earth's gold sank billions of years ago. Despite this, massive open-pit mines continue to extract vast quantities of gold from the surface today. If the crust was wiped clean during planetary formation, where are these modern mining operations actually getting their supply? For decades, geologists pointed to the Late Veneer hypothesis. Long after the core formed and the outer crust began to solidify, Earth was bombarded by a massive wave of meteorites. That meteorite dusting explained the surface deposits and reinforced a long-held assumption. Whatever sank to the deep core 4.5 billion years ago was locked in a permanent, isolated vault. That assumption held until researchers started sampling fresh lava from deep-source volcanic regions, like Hawaii and Iceland. The magma feeding these specific sites originates from the deep interior, and it carries chemical signatures that didn't belong in the standard model. Intrigued, the composition of these rocks couldn't be explained by a superficial dusting of meteorites. The anomaly forced scientists to consider that the core's vault might have a leak. The magma erupting at these specific hotspots doesn't come from the shallow crust. It is fed by mantle plumes, massive columns of superheated rock rising all the way from the boundary where the rocky mantle meets the liquid outer core. To figure out exactly what these plumes were carrying, scientists needed a forensic marker. They turned to ruthenium. Like gold, ruthenium is an iron-loving siderophile, but its isotopic variations depend entirely on its place of origin. This chart contrasts the two possibilities. On one side, the ruthenium isotopic ratio found in meteorites. On the other, the ratios in deep-source volcanic rocks. The deep-source lava fails to match the meteorite baseline. Instead, it perfectly matches the primordial signature of Earth's deep interior. This points directly to the core mantle boundary, nearly 3,000 kilometers down. Down there, temperatures exceed 5,000 degrees Celsius. The liquid iron outer core is churning, and the solid mantle is slowly creeping, creating a highly active mixing zone. Under these extreme conditions, tiny fragments of the core's outer edge can cross the threshold. Once they enter the mantle, this material gets caught in convection currents and creeps upward, embarking on a journey taking tens of millions of years. This ruthenium fingerprint provides physical evidence of a slow-motion geological leak. The core is actively releasing trace amounts of its ancient contents into the mantle. While these eruptions are violent and fiery, they do not produce rivers of pure molten gold. Viral headlines suggesting otherwise miss the scientific reality. There is also zero chance of tapping into the source. The deepest hole humans have ever managed to drill reached 12 kilometers. Pushing a drill bit through 2,900 kilometers of solid rock and crushing pressure remains purely in the realm of fiction. What actually makes it to the surface is measured in infinitesimally small, trace amounts. This material is economically worthless, yet for geochemists, it is a priceless record of our planet's heart. Stripping away the sensationalism reveals an important shift in our understanding of planetary mechanics. The core is an active participant in Earth's chemical evolution. This discovery reveals that the rocky mantle and the molten iron core have been chemically communicating for billions of years. This deep Earth convection acts like a conveyor belt, pulling chemical records from the most isolated depths of the planet and carrying them straight to the surface. A simple piece of volcanic rock from these sites represents the physical endpoint of a 100-million-year journey from the very center of the world. The realization that our planet's deepest, oldest layers are still reaching out to the surface proves that Earth's greatest mysteries are still unfolding right beneath our feet.